Okay, so what we were looking at so far is we were looking at how to slow down the clock, because we want our clock to only have, say, 5 cycles per second as opposed to 100 million cycles per second. And so we have this code that we were already given, and we want to change it so that it just toggles the clock every or 5 times a second. And if we assumed a system clock of 100 million hertz, if we divide that by 5 that we want, we get 200 million. And so we just put that in here as a parameter. We said, was it 20 million? Sorry, 20 million. We put that in as a parameter. We said x equals 20 million. And when the count gets to x, that's when we're going to toggle it. But we have to be careful about one more thing on this one that caught me, that I couldn't figure out why my code wasn't working. And I have this as question number 3. Are there any other changes we should make? And my hint was, what is the size of the variable count? So if you look up here where count was defined, how many bits is count? If it's 19:0, how many bits is that? That's 20. What's the biggest number you can have with 20 bits? Yeah, I mean, it's whatever 2 to the 20th minus 1 is, which seems like it'd be a pretty big number, but two raised to the 20th is less than 20,000. And so if we're going to say, if we're not going to do anything until, 20 million. If we're not going to do anything until x gets to 20 million, and we don't make x a big enough variable to get to 20 million, nothing's ever going to happen, which is what happened to me for a while until I realized that. So we need to make x have enough bits to be able to be 20 million. Now, there's a couple ways to figure out what that could be. One is just trial and error, just raise 2 to various powers until you get something bigger. But the other way is if you take log base 2 of a number, that would tell you how many bits you need. And if you have I didn't start it. If you have a TI-84 and you press the math menu, there's a log base where you can do log base. If you don't, on any other calculator, you can just do log 20 million divided by log 2. And that's using the change of base formula for logs. And so log any base of 20 million divided by the log of 2 gets us what log base 2 of 20 million is. And that would be the power you would raise 2 to get 20 million. And did anybody do it on their calculator? So this, you want to do this, or on a TI-84, press the math button and then go down to log base and then do log base 2 of 20 million. 20 what? 20.93. Really? Yeah. Are you using? I hate that calculator. I cannot stand that calculator. Is that the little thing that y'all have to use like in calculus and is that?
Oh, it's just some other calculator.
Oh, okay. So did you do natural log of 20? Maybe you forgot a 0. A natural log of 20 million, that's 7 zeros divided by natural log of 2.
Oh, yeah.
Okay, so you should have gotten 24 point something. So that means we want 25 bits. So you want to change this reg for count to 24:0, because that goes 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 24. So reg 24:0 count, semicolon. And that should probably be all the changes you need to make to this. Now, what is the difference between, so we have this now, and what is the difference between CLK and clock with a capital C? So when you look at this code, what's the difference between little CLK and clock? What's the difference between those two?
What was the internal clock?
Yeah, so this one is the system clock. It is if you connect it to the system clock in your constraints, but that's what we're assuming. We connect it to our system clock, and this is the clock that we made. And so if you instantiate this module, if you instantiate this module, then you have now made a clock that has 5 cycles per second, and you can access it. So when it says what aspect, I didn't know how to ask this question. What aspect of this module will you need in your counter? You are going to need this capital CLOCK. That's going to be the clock you use. So whenever you say at positive edge clock, we're talking about this clock, because we want that to be the one that we actually use. Because if you use CLK, little CLK, that's attached to the system clock, then it'll be too fast. Okay, so are there any questions before we go on and look at the code for the counter? All right. So in the lab instructions, he says to use figure 5.53 to base as a base for your counter, and he said, I have it somewhere. What were his instructions? He said, first build a 5-bit counter similar to the one shown in 5.3.3 of the text. Let this base counter with load be a module called alpha beta counter. So you're going to call yours your initials _ counter. And he said we wanted it to be 5 bits. So we'll actually get to that in a second. So the first thing question I have here, number 2, we will not use reset in. How will that change the code? Well, we don't need reset in. So first of all, we can just take it out. So out of the list up here, and then also out of the sensitivity list. So we're going to change this to just be always at positive edge clock. Now let's look at this. Is that the clock we want to be using?
Which one?
Right here. Is this the clock we want to use for our counter? Do we want to use that clock, or do we want to use CLK? Yeah, we want to use that clock. And then since we don't have if reset in, we're not going to have this part anymore. And so this first else if is not going to be an else if, it'll just be an if. It'll just be if L. Okay, so those are the changes you would make to take out the reset in. Okay, how many bits is this counter?
Or that one's 4.
This one's 4. And we need to have a 5-bit counter. So how do we change this to a 5-bit counter? Change the 3 to a 4. in both of these places. And we'll talk about that in a second. So what R is what you load when you restart the counter. Now, we could have not used R at all and just assumed we were going to load 0. But this makes it a little more flexible so that if you end up having to have a counter where you don't go back to 0, you can change that. So R is what you load when you restart the counter, and that's going to be something that you send it from your main code. Q is your output of your counter. That's the actual count sequence. Q is going to be 1, 2, 3, 4, but in binary. So we needed to change both of those to 4 to get a 5-bit counter. What if you wanted a 3-bit counter? What would you do? 2, right. Okay. What part of this code is used to load a new value? So this right here is the part that you use to load. So it says if else. So when you want to load, when you want to start over, when you want to give it a new value, then you need to send it a value of L equals to 1. So when L equals 1, it'll start over with whatever you're telling it starting over is. Otherwise, if L is not 1, every time it adds 1 to Q. And that's what this part is. This E is the enable. So the enable means if your clock is enabled. If you want it to be counting, then count. But we actually need to have a way to make it stop, but not start over, just freeze in place, because it says I don't remember, it's in here somewhere, but it's basically that as long as enable is 1, it should keep counting and your light display should keep going. But if enable is 0, then it should just freeze where it is. And so we need to have one more thing in here to tell it what to do if enable is 0. I'm not sure what would happen without this. I think it wouldn't work. I'm not entirely sure. I didn't try it. But this is going to be, so we have if L. So if L, then you load. Else, if E, if it's enabled, then you count. And then the last part we're going to have is just an else. And we just send Q back to itself. Again, seems like that shouldn't be necessary, but it works. So, let's see. Oh, but we do have a problem here. And that is that as written, it doesn't know to use our new clock, even though it has that capital C in there, because we have not instantiated that clock. We have not made a copy of that clock yet. And so we have to tell it, we have to instantiate that clock, our clock. So you want to go back and look at your clock code, and you see that there's 2 variables here, CLK and capital CLOCK. And so when we make a new clock, we could give it a name. I just did right in here. So right here. You say what the name of the module is that you are instantiating. This is clock div. My guess is that was standing for divide clock. And then you send it the parameters CLK, that's the system clock, and then capital CLOCK, that's the variable name that we're using. And so what that means is that I have the wrong variable up here in my input list up here. This input should actually be little CLK, because when I start this, I haven't made my clock yet. And that means that this input should also be CLK. And I probably need a wire. Let's see. Yeah, wire. Because I'm using clock in here with the capital CLOCK, it needs to be something. It's not an input and it's not an output. It's something that I'm using within this module here, and so that would be a wire. And so just put it in right in our list up here of other variables. You'll just put wire, capital CLOCK, semicolon. Okay, how are we going to use this load feature to make a mod 16 counter? So if we have a 5-bit counter, that can count up to 31. We're supposed to make a mod 16 counter, which means it goes 0 to 15 and then back to 0. 0 to 15, 0 to 15. The way I did it, I'm now done with this. I have a good general purpose counter that I can use, that I can make into a modulo counter somewhere else. But how am I going to do that? When it comes time to make a mod 16 counter, how am I going to do that? Okay, and to what?
To make a parameter for each, how many bits it is.
And then how is that going to, what part in here is the part that's going to tell it start over your counting?
Like a certain, whatever part of the vector is the one.
Right. So
So
I'm
it goes
gonna
before
find that somewhere else in my main module, and then what do I need to tell this module to actually start over? Yeah, I need to tell it when I'm ready for it to do that. I need to send to it. I need to say L equals 1. I need to let it know that L equals. I need to change L equal to 1. So that it'll do this step in here, and I need to let it know what I want R to be, which is generally going to be 0 to start over again. So from the module that's calling this, when I'm ready to, when I detect what you're talking about, when I do that detection, at that point I set L equal to 1 and I let R equal 0.
But you would write that part in the main module?
Yes. That's what I did. I think there are different ways to do it, and it wasn't clear to me from his instructions if he wanted you to do that in here or if he wanted you to do it from the main module. Because the instructions said, first build a 5-bit counter and let this base counter with load be alpha beta counter, which to me sounds like really general. And then it says in building a modulo X counter, but it doesn't say where to do that. So you could do it in here as well. You would have to send you would do what we're gonna do in the main module, you would do it in here instead. You would put your parameter for your mod base in here. Okay, so are there any other questions on this part? Yeah.
So, can you explain why we changed the capital clock to locus CLK?
Yes, because this is my list of actual inputs and outputs. And as far as this module is concerned, the capital CLOCK is not an input or an output, because little CLK, our system clock, it's actually the input, because it needs to be input into our clock module. But so it's the input for the clock module, so it also has to be an input for this module, because we're making the clock in here. So we have to have the actual input here. And then the capital CLOCK, that's not an input. That's something that this clock is making within this code, and we're only using it within this code. We're not exporting it anywhere else. And so it's just a wire for within this code. Okay, other questions? Okay. So now you have to create your main, what I would say is your main code. This is what does this stuff. And it turns out, with what we've done so far, that it's not actually that hard, because all the hard work has been done.
Just have to include all the LEDs, whenever it's set to high and low and everything.
So, first we need to think about let's see. So you're going to have your module, and you're supposed to call it your initials comb1, and it's 1 because you're going to make different versions of this in the lab. Okay, and then my first question is, what inputs and outputs do you need? So I made we from this code here, we are going to instantiate a copy of this, our counter, which instantiates a copy of the clock. So things that are I'm going to send to one of those two things, I need to include those here as well, as either inputs or outputs. So, for example, R. So R, I'm going to make R for this one be an output, because I'm going to create it to send it to the counter. The same with L, because I'm going to create that and tell it L is either going to be 0 or 1, depending on if we need to load or not. Can anybody tell me, I have 3 other things here that I have as inputs or outputs. Anybody want to? What's that? That's going to be listed down here, not as an input or output. It's going to be a I'll list it as a type of that module. CLK. LED. And I recommended in my notes to just call it lowercase LED because there's 16 of them, and if you use the constraints file, the template that he already wrote, he calls it lowercase LED, and so that way you don't have to go in and change the names of all 16 of them twice. So I would just call it LED. And one more, it's going to be a switch to enable E. So our inputs are E and clock, and I have output. Now I'm going to be changing things inside an always block, and so I need to declare them as reg. And so my first time through, it's 5 bits, so I'm going to make R 5 bits, so output reg R. I'm also going to have in my always block, I'm going to tell it whether L is 0 or 1 to load. And I'm also going to have as an output my LED. And I did it 15 to 0 LED, and when you do that on your board, I did not bring the board with me, but from left to right, this one is 15 and this one is 0, so when you create your patterns, it'll be in this order. Okay, so we also are going to have our count. And our count is internal. It's not something that we are outputting, and it is kind of something that we're inputting, but we're getting it from another module. And I'm going to call that a wire, and that's Q. And then we're going to have a parameter, and this is going to be our modulo. So this is going to tell us how much we want to count before we start over. So the first time through, what you have to do for your pre-lab, you wanted modulo 16, which means x equals 15. In the lab, you're going to change that to different values. And then the last thing we need to set up here is we need to make a copy of that counter. We need to actually have that counter. And so what was it called? It was called RR counter. And in order, I had R clock ELQ. Okay, so what that line does for me is that gives me Q to work with. If I didn't have that, I wouldn't actually have my count. So this is, I give to the counter R, the clock, enable, and L, and the counter gives back to me Q. And then all we have left is to tell it what to do with that count. So we want something to happen every time we have a count. So that's just going to be always at Q. So we need to check to see, do we continue to count, or do we need to start our count over? So how do we check that?
Case statement?
We're going to get to a case statement in a minute, but we only have one. We only have to check one thing. We're only checking, is it at a number or not?
So it's an if statement?
It's just an if statement, yeah. And so if, and then I set my parameter x, I want to check to see if it equals x. Because that's what I set for my stopping point. Now, go ahead.
I thought that X was that parameter that we set in the count, like the first.
It's a different module, so it's a
For the
different
call?
parameter. So
Okay.
even though I'm being very sloppy with using the same variables all over the place, this is actually a different variable.
Okay.
They are different. If they're in different modules, they're actually different. But yes, I used the same variable name.
X is 15.
X is 15 here. Yeah. Okay, so what do I want to do if Q equals 15? And I ended up wanting to do more than one thing, so I have a begin here. For my always, actually, I think I need a begin for my always as well. Yes. So. Okay, so if I've reached where I want to stop counting,
You load the equals 1.
that's right, I make L equal to 1. Because L equal to 1 will tell the counter that to load instead of continuing to count. And this could have been a constant. I don't have to. I'm going to put the R first. Because I want to set what R is before. I tell it to load R. I want it to know what R is before I tell it to load it. So, you don't have to put 5 zeros there. I'm saying R is the 5-bit binary number 0, and that's what I want it to load. You could have just set it to load 0 if you wanted to. Okay, so that is if Q equals X. If Q does not equal X, else we need L to be 0 because we don't want it to load. And then the only thing left to do is to set your LEDs. So depending on what count you're on,
Is that in the same always block?
this is in the same always block, yeah. We actually only have one always block here. I thought I was going to end up having 2 like normally with finite state machines, but it works with 1. Okay, so based on Q, whatever Q is, so wherever we are in our count, we are going to have a different pattern of LEDs. So when Q was 0, then the LEDs were all supposed to be dark. And I will be honest, I didn't really try different things here because I just wanted to see, I wanted to visually see what was going on. I don't know what happens. I really should know. I don't know what happens if you tell it you want a 16-bit binary number, then you only give it 1 digit. I think it works fine. I think if I had just said 16 binary 0, that would have been fine. But what this is showing all my LEDs in order and how I want them to appear. And zeros mean not lit up. And so this is just visually, you can just see exactly what you're going to get. So if I had, I'm not going to fill them all in, but let's say I had case 5. In 5, I want the first 5 lit up, at least if I'm reading correctly what he wanted it to be. Yeah.
But these, aren't the ones not lit on
That's for the character, the 7 character display. Yeah, yeah, it's confusing. But for here, the ones are lit up. And so I think the idea is when you're at 0, none of them are lit up. When you're at 1, the first one, and then 2, and then 3, and then 4, and then 5. So it fills up until you get to 16. And then you do want to have.
If that begins before the 0 and ends at the end of the LEDs.
You don't, because it's just a single line, a single statement. Yep. So you can see here how I have it, just blend it. And then you do want to have a default. And for my default, I had them all lit up. No, I had them none lit up. Yes. So I had, oh yeah, and so now I have the answer to my question because I did do it. Because at this point I was tired. Yeah, and just like that. And then you can end your case. So end case. And we're ending the always block and end the module. Okay, so that's your main logic part. So is that questions on that? How that works? All right. So the last module you need is the module that ties everything together. So, and you're supposed to call that top. So, RR top. And I had, when I completed this project, I had 2 inputs, 1 output, 2 wires, and 1 instantiation. So all I really have to do here is tell it what my inputs are, what my outputs are, and to instantiate any other module that I need to instantiate. So, what do y'all think? What do you think we need here? Overall, big picture, when you're looking at just not the individual modules, but just like overall, what things are actual inputs?
So the top one?
Right, because the top module is everything put together. What? The clock. Okay, and then there's and the enable. And what's your actual output? Your LEDs. Which was just a single variable, a single vectored variable. So that was LED. And that was it. So we have 2 inputs and 2 outputs. And so our input, clock and E, and our output was a 16-bit vectored signal called LED. Okay, now if we want this to do anything, we have to tell it what to do. And that means we need to tell it, we need to instantiate one of these other modules that we've made that's going to do something. And which module would that be? Yeah. So that was yeah, COM1. I'm going to put it down here because I need to do something else first. So, mine RR COM1, and then I need to look and see what my inputs for that were. I had RL clock LED E. Which shows me now something that I'm missing, because if I'm instantiating this and in my list here I have R and L and I don't have R and L as inputs or outputs, well then they need to be wires. So and that's all you have to do with your top module.
Why do we not have to call the other ones?
Because this one, COM1, calls the counter, and the counter calls the clock. There are lots of different ways to do this. This is not the only way to do it. So you certainly could have done one in a way where they're all listed up here. On this, it seems to me, the way that we have this drawn here, that you have the system clock is going to your clock module, which goes to your counter module, which goes to your COM module, and then all together that's in your top module. So I'm not guaranteeing that I'm right about everything. I know it works. I mean, I did it and I programmed it and it works, but I don't know if I am following the instructions correctly. So I hope I am. Okay, so the last thing to talk about are your constraints. You don't have to have these in your pre-lab, but if you have them set up ahead of time, that saves some time. And for this lab, they're really easy. You do have to set up, I'll just show you this. You do have to set up Okay, so you do have to set up the clock. This is not the clock that you used in the lab last week that had the four buttons that you plugged in. This is just the actual system clock, and I think this is the one he has in his constraints file. If you go to lab resources. Yeah, so this is the one that he has in his template. So you can just take this one right here and uncomment it. You'll need one switch for your enable. I chose the bottom one because that was the one all the way to the left, but you can choose whichever one you want. And if you call your LED LED, then all you need to do is uncomment all your LEDs. If you decide you want to call it something else, feel free. I wouldn't. Yes?
The first one is the LED all the way to the left or the right?
LED 0 is the one all the way to the right. And so that's why I have it set with I put 15 in front here. And so that the first number in my pattern is the one on the left. I get my left and right backwards, so I may not. Here's the board. Here are your LEDs. This one is 0, this one is 15. And when you write your pattern like we have here, this one is 15 and this one is 0. So if I wanted these two lit up, I would have my first two to be 1s.
So you can go either way with the pattern. You could go that way.
Yeah. Yep. And oh, on the template file, don't forget when you pick whichever one you want to be your enable switch, don't forget to change the name to E. And I find when I have errors, a lot of times it's in my constraints file. Okay, so any questions before we go on to some problems? Yes?
What did you say about the clock that we use for different things?
Yeah,
Is it
it's the regular clock that's in his template. It's right up here, it says clock signal. You'll just uncomment it, and the name of it is already CLK. So it's already the one you want. Okay, so now let's take a look at some problems with finite state machines. Let me stop this recording.